So today we're gonna talk about the third best thing about putting Linux on Snapdragon laptops, with number one being performance, number two being lots of features and free battery life, pretty much. So my name is Konrad. I come from Poland. I've been a contractor with Lenovo for a year and a half and then some. And I've been in the putting Linux on phones game for quite some time. And that basically led me to being a co-maintainer of Linux ARM MSM and some user space tools associated with it. So, as you may know, as you probably do know, modern computers are full of different cores that are not necessarily executing code like normal CPUs. You may have various DSPs, ASICs, some microcontrollers like ISPs, and all of them require power. And it should come as no surprise that with that amount of silicon on board, the CPUs themselves may not be the main power consumer. And it often is the case, especially if you have like 5 or 6 cameras running, which is nothing special nowadays. So our problem is, since computers run on electricity and they need to do work, they require energy. And as the Joule-Lenz law says, if you do work, you output heat, and heat is not good. And we can make very quick and simple observations that reducing the current would reduce the heat output. But reducing the current is rather hard because that comes out as a certain characteristic of the silicon, and we can very rarely alter it. But a more important observation is that reducing the time also reduces the heat output and the energy consumption. But it turns out that not computing also consumes power. So back in the Windows 95 days, and way before that as well, the computer would consume about as much power as doing work when just idling, because there was no notion of CPU idle or things like that. Today, if we had the same situation with 64-core Ryzen SKUs that eat 500, 600, 700 watts, you would burn your house down and go broke with your electricity bill. So that's just unacceptable. So CPU idle was invented, and the basic premises are turn the CPUs off or put them into some sort of a not exactly full throttle state if we're not using them. Do it really often, because every microsecond counts, and do it really fast, because we cannot afford to have a core that's dormant for 3 seconds when it could execute billions of operations in that time frame. And the idea of returning from CPU idle is all sorts of wake-up interrupts, be it IPIs or interrupts from one CPU to another, or at least one wake-up interrupt from the system to tell the CPU cluster or socket or whatever other contraption that it needs to wake up and do work. And historically, it's been hard, and especially so on ARM. And our solution seems to be adding even more cores. And that is because CPU idle is difficult. It must be very robust. It is absolutely silicon specific. So every time there's a new core, new generation, new implementation, you need new code to handle all the power sequencing, all the take out of reset, go into sleep routines that need to take place in very specific order. And there may be quirks that are not exactly compatible with Linux, Windows, any other OS. And if you fail, the machine will likely stall and hard reboot. And that's obviously not great, especially if we're talking about automotive. So on Qualcomm CPUs as of late, we've been having the pleasure of working with PSCI and CPU idle in the way that's ARM standardized. So the only thing that we have to care about is providing the right magic PSCI values to basically describe which sort of suspend state we want to enter on a CPU or a cluster. And everything else happens on an MCU that's not controlled by Linux. And same goes for CPU FREC. We only have to request something akin to ACP/IP states, so a tuple of frequency, voltage, cache parameters. This is all handled by said MCU, and this is great because 10 years ago, all of that would have to be in Linux. And with things like variable voltage per chip unit, so my Snapdragon of the same model and your Snapdragon of the same model may require different operational conditions because of silicon lottery. Handling that in Linux is so simple that for one generation, we still don't support it 10 years later. And as for off-CPU IP, most of the power management happens on what's known as the RPMH core. It stands for runtime power management or resource power management, sorry. And it's basically a black box. We talk to it in a secret language that not everybody seems to understand, even us who work with it, which is fun at times. And it accepts a sort of list of requests which parts of the SoC need to be kept on and how it does it. We don't care in the slightest, which is fantastic. And it also helps us coordinate a SoC-wide sleep state, which is called power collapse, where the CPU is off, all of the auxiliary cores are off. We can even cut the power to DRAM, say for the refresh line. And it helps us do things like SoC independent code, because we only have to add a single driver to handle this RPMH architecture, let's call it. And everything else it lives in the firmware that we don't have to care about. And as it says on the bottom of the slide, this must be very robust, because if you fail to set a voltage or do it improperly, the SoC will crash again. And that's not good. And we don't want to fight with this. So moving this away from Linux and Windows and any other OS is basically what we want to do. Continuing, RPMH has this notion of masters, which is basically clients. And each one of them can send a request, which is just what you think. And that would keep a resource online. A resource is a vague by design term to describe any sort of hardware that is managed by that core. This can commonly be a clock line, a regulator, perhaps a GPIO, or maybe a complex of some of those three. We don't know, we don't care. And example masters can be the CPU subsystem, all the DSPs, the camera, PCIe islands, and that list grows every now and then as the parts of the SoC become more and more independent with each generation. So the best way to go about this, am I muted? Or it's okay. Is to only keeping things online when absolutely necessary and at the lowest power state possible. So we can turn everything on at the max state, which would give us perfect stability because nothing would ever be unclocked or unpowered. But that would, of course, defy the point of having runtime PM and all of the power management. So we do our best to try and request the, again, SoC-specific values for each hardware, for each IP. and we commonly describe it in the device tree or ACPI, or well, ACPI is supposed to do it, but let's not talk about it. And after aggregating the data and basically taking the maximum of all of the requests for each resource, we send it to our PMH, and it sets the maximum across what Linux requested, what the DSPs requested, what any other software running on any other core requested, and does the power sequencing. And if we fail to provide the required power and required clocks, the system will die. So we have to be careful, because the default behavior in Linux, as we talked about during previous presentations, was, or rather is, if something looks unused to Linux, then we should turn it off, because why should it waste power? And that's generally very good, but that requires very high scrutiny, because if you fail to mention that this clock line or this regulator is necessary, then Linux will never hesitate to just turn it off for you, which may result in your screen going black, your device crashing, or any other undefined behavior that you may find out after a tough debugging session. And the worst things that happen are missing links. So think of the SoC as a town that's connected by routes, and if you happen to close a route by not enabling the required paths that connect one to another, that may not be direct, they're usually not direct, you will not, for example, be able to communicate between the CPU and, say, the camera, because it's physically disabled. The most common pitfalls that happen to us developers when doing this are listed here. So it's missing interconnects, clocks, regulators, and power domains. That's how they are described in the device tree. And usually when that happens, the system will reboot immediately after the unused cleanup is done, because something is probably requesting the hardware that is behind all of those. But the default behavior on unclocked access is just a straight hard reboot. And continuing, we can do all the best to sleep properly, describe all the required resources, and we also have to keep in mind that this unused cleanup is absolutely necessary, because, for example, the SoC may have 4 PCI controllers, but our device may only have a Wi-Fi card and an NVMe drive, and the other 2 controllers are unpopulated, not connected to anything. So the bootloader is common for all devices using a given SoC up to some point. So it stands to reason that it will power up all 4 and scan whether there are any devices. But it's usually the case that it doesn't shut down the host that it powered up, because I think Windows requires to keep it on. There's some legacy reasons for that. And so we have to do it ourselves, because every unpowered resource will lead to blocking of sleep and wasted power and wasted heat. So we should take care of that. And runtime PM is also very important, because there are some drivers that have 5 milliseconds timeout before they go into automatic suspend. You may think that's crazy, because it takes like a couple hundred milliseconds to do the suspend and resume routines, but the power draw from them is so high that it's actually really smart to turn them off as soon as humanly possible. And also can't forget about scaling down the frequencies, and keep in mind that even if you did everything correct, you may not be able to hit the lowest power states because Linux is not the chief. RPMH makes the final decisions, and Linux can basically prevent the system from sleeping. It cannot say, go to sleep right now. And it's easy to spot some similarities. If you do not have any outstanding votes, RPMH will just go to sleep because similar to the unused cleanup mechanisms in the Linux kernel, RPMH has basically something like that. If the resources are not used from its perspective, it will just clean them up and shut them down. So if everything goes well and we go into this power collapse state that I've mentioned before, so the SoC-wide suspend, we can drop down to milliwatt level of power draw compared to multiple or even 10 plus watts at runtime. And by the way, if we're idling at runtime, so just display on, nothing on the desktop, my X13S laptop takes 1.7 watts, I think it is. There's still room for improvement, but word of a difference between 1.7 watts at runtime and closing the lid and getting a few milliwatts of power use. So the things that we have to improve as the kernel developers is basically go over all the previous platforms and make sure that the lessons we've learned with the new ones are applied to all of the previous ones, because I don't know if you've noticed, 80% of the code is shared between all Qualcomm platforms dating back 5, 6, 7, 8 years. So fixing a bug in one will very often lead to fixing a bug in all of them, or at least improving some things. And it's not like we don't care about the older platforms. We just have to focus on the newer ones. And because the list of not currently active development platforms only keeps growing, it stands to reason that we may not have time to, every time we discover a bug, validate it on all the hardware that we may not have at this point because it was considered obsolete. We should also definitely improve common code, as I've said, and the latter part of the second point is even more important. Ensure that nothing that is not absolutely necessary is enabled, because that's just a power hog. And perhaps just as a general mindset, the feature gap may not be so important, especially in the state that we are in right now, where almost everything works for me on this 8280 laptop. But the power situation, it could be improved. We can already do over a day of closed lid suspend, but I know that it can do much more. And that's all. Are there any questions? Okay, so I also have a bonus slide. A proper suspend cycle would look like this. So the user gets the laptop or phone or whatever. The OS boots successfully and manages to clean up all the resources. The user does some things, I don't know, checks their email, then clicks the sleep button or shuts the lid. Every piece of hardware is disengaged, disabled, powered off. And at the very last stage, the OS propagates a magic value to the trust zone where the magic happens. And that, in collaboration with RPMH, does the black box thing, and all the power rails are powered down, the ones that we can. Again, DRAM refresh and things like that need to be powered on, because otherwise we lose state. And we can even cut the system crystal oscillator to some point, which just gives us additional milliwatts to spare. and the AOSS, which is the always-on subsystem, the place where the RPMH core is located, enters a retention state. They couldn't call it off because it's called always on. And, you know, the computer just sleeps, probably somewhere on a shelf, and then when the user opens up the lid or presses a button on the keyboard, the always-on subsystem gets a wake-up interrupt, and basically all of that is unwound, and we're done. Thanks.